Hello, everyone. Welcome back to the Beyond Clean Cases or Crisis ASC conference. We are so glad that you're sticking with us for the day and spending your Friday with us. Our next speaker is Dr. Bryan Kirk. He is the director of Bryan Kirk Sterilization Consultancy Group Limited and worked for 3M for 30 years. And he's actually going to continue the discussion that Larry Talapa began about hydrogen peroxide. Dr. Kirk will be discussing the newest scientific evidence in monitoring tools for hydrogen peroxide sterilization. And I'm really excited. Dr. Kirk, it's 7 p.m. your time. We're so thankful that you're spending your Friday evening with us. And with that, I will hand it over to you.
Well, thank you very much for that kind introduction. And hello, everyone, wherever you may be. As Lindsay mentioned, my time here in the UK is 7:15 in the evening, and I'm really looking forward to doing this presentation for you. So if you have any questions, we'll try and cover those at the end during the Q&A session. So the title of the talk today is Monitoring Tools for Hydrogen Peroxide Sterilization. And we'll consider some new scientific evidence around that subject. So I'm just going to advance through a couple of introductory slides. So again, my name's Dr. Bryan Kirk. I've been working in this industry for over 40 years in various guises. I worked in the UK National Health Service for 10 years as a quality assurance pharmacist. And I then worked for 3M for 30 years. As part of my activities during that time, I became a member of a variety of standards setting bodies such as BSI, CEN and ISO. I'm actually now the convener of the Working Group 3 for moist heat sterilisation. And I also do some work for the University of Nottingham, and they very graciously awarded me an honorary associate professorship in the Department of Food Sciences, where I do my work. So I was very pleased to receive that. So let's look at the contents of this presentation. Well, we're going to, first of all, do a very brief outline of hydrogen peroxide sterilization processes, and then we'll consider how such processes should be specified, validated, and then routinely monitored. And then we'll consider how we can assure that the sterilization process is effective. And that will include a consideration of physical, biological, and chemical indicator technologies for monitoring the hydrogen peroxide process. And then near the very end of the presentation, I'm going to ask a very fundamental question in relationship to the performance of chemical indicators. And that will be, do all chemical indicators of the same type perform the same? And during that section of the talk, I'll consider the scientific evidence that's recently been published looking at the performance of some commercially available chemical indicators. So let's first of all have a very brief outline of vaporized hydrogen peroxide sterilization. But before we do that, let's consider some very basic definitions. The first is sterile. What do we mean by sterile? Well, the absolute definition for sterile is free from viable microorganisms. And sterilization is also a fixed term, and this is a validated process used to render product free from viable microorganisms. And both of those definitions can be found in this ENI standard 11139, which is the compilation. It's a bit like a dictionary of all the terms and definitions that are used in the suite of sterilization standards that the ISO standards organization publish. So that's actually quite a useful reference document if you want to try and understand what a particular term means with respect to its use in sterilization. So sterilization can be achieved using a variety of processes. And this slide tries to segment those processes into different categories. And on the left-hand side, we have physical processes which kill microorganisms by virtue of a physical action. So that's subdivided into hot processes, such as those which would use steam, moist heat, or dry heat. And then we have cold processes employing UV light or ionizing radiation, such as gamma, E-beam, or more recently, soft X-rays. And these are used quite a lot in the industrial sector for sterilization of large loads of single-use medical products. And then on the right-hand side, we have segmentation according to microbicidal action by chemical agents. And I've subdivided those into alkylating agents, such as ethylene oxide, low-temperature steam with formaldehyde and glutaraldehyde. And then that central green portion, the oxidizing agents, such as hydrogen peroxide in its various forms, chlorine dioxide, peracetic acid, and ozone gas. And of course, for those that are working in the hospital sector, then steam or moist heat sterilization is the most prevalent sterilization process used for reusable surgical instruments, a set of which you can see in the picture near the bottom of the screen. So let's now consider some low temperature sterilization processes and its utilization in healthcare or hospital practice. Well, ethylene oxide is a good example, and that's been used in hospitals for many, many years. Its use is country specific. I know it's used quite a lot in the United States, and it's also used quite a lot in Southern Europe. But you don't find it very often, certainly in the hospital sector, in Northern Europe or the United Kingdom. They tend to use other technologies. Ethylene oxide, of course, is used extensively throughout the manufacturing industry for the production, large-scale production of single-use plastic-type medical devices or some bespoke products such as these heart pacemakers that you can see in the picture there. Low-temperature steam with formaldehyde, LTSF, is a very old technology which has been used for many years. If you visited a UK department 20, 25 years ago, you would almost certainly find an LTSF machine. But nowadays, it's largely gone out of favour. I do know that the Central European based sterilizer manufacturers are doing a lot of development work in making that process more efficient and more attractive to users. So I know that LTSF is used in Central European and Northern countries. But also I know that in the US, it's not considered a sterilization process at all, but rather a fumigation process. So it just goes to show that we do have significant regional differences in the way we do our sterilization. Now, hydrogen peroxide, VHP, is, I've called it the growing technology, but I think it's probably a grown technology. It's been around for 10, 20 years now, and it's probably the go-to low-temperature sterilization process that practitioners will look at when they're considering purchase of a low-temperature sterilization technology. Many hospitals are obviously now using it, and there are growing areas of application, for example, in endoscopy. And I always use this quote from Professor Tony Young, who gave a talk at the IDSC conference in 2010. It's obviously 10 years ago now. But he said, as the field of endoscopy develops, there will be a greater need for sterile endoscopes. And I think with recent incidents that have been reported in the press and in the scientific literature, then that statement could never be further from the truth. So here's the first polling question, which you can all engage with. The question is, do you use a vaporized hydrogen peroxide sterilizer in your department? And what I mean that is, for example, an ASP Sterad machine, or a V-Pro, a Matachana, a Cheese, or a Gettinger, a TSO3 type low temperature hydrogen peroxide sterilizer. So I'll give you a few seconds to answer yes or no on that question. So if we take a look at the answer, 81% of people are using hydrogen peroxide. So I think that is confirming what I said earlier, that hydrogen peroxide is indeed the sterilization method, low temperature sterilization method of choice nowadays. So let's have a quick look at the Vaporize hydrogen peroxide process. Well, the process itself basically uses hydrogen peroxide as opposed to some of these other technologies which are used to decontaminate rooms, which tend to use aerosols or fogs of hydrogen peroxide liquid to basically surface decontaminate rooms or surfaces or devices in a hospital setting. And the hydrogen peroxide process can basically be used as a pure vapor on its own, or it can have a plasma phase associated with it, which might take place either before the hydrogen peroxide exposure period, in which case it might be used to preheat the load, or it can be used at the end of the exposure period, in which case it will be adding a little bit of microbicidal activity, but it's also degrading the hydrogen peroxide to non-toxic oxygen and water. So it's acting essentially as an aeration stage. And then there are other processes which use hydrogen peroxide vapor mixed with another microbicidal gas, such as ozone. And you can see in the picture that it's quite a complex process. This diagram is actually showing you the pressure transitions that are occurring in the chamber during the process. And you can see that there are multiple pressure changes that might be repeated once or several times in order to effect the sterilization process. And essentially, there are two dominant manufacturers in this area. One is the ASP Sterad machine, and the other is the V-Pro, the Steris V-Pro machine. But nowadays, there are other choices. And if you look towards Europe, you will find that many of the European sterilizer manufacturers, such as Matachana, Cheese, Gettinger, are producing and offering vaporized hydrogen peroxide sterilizers. And also, if you look further afield, down towards the Far East, you will find a lot of Japanese and Chinese manufacturers also offering this kind of technology. Now, one of the important elements or features of the this sterilization technology is that it is a truly low temperature process. So it can be used at 30 degrees up to 50 or often 60 degrees C. Typically, these modern machines used in hospitals will be operating at around 50 degrees C. And the cycle times are anywhere from a few minutes, maybe 30 minutes, up to 100 minutes. And really the cycle time depends on the type of instrument or equipment that you're trying to sterilize. Where you're trying to achieve simple surface sterilization of a relatively simple medical device, then you will be able to use a very quick process. Whereas if you're trying to sterilize a lumen instrument, such as an endoscope, then you would need to use a longer process in order to allow time for the hydrogen peroxide vapor to penetrate down into the lumen and effect sterilization. Limitations in the process. As I mentioned, there are restrictions on the length of lumen that you can in fact process in these machines, and generally the longer the lumen and the narrower the lumen, the longer the time it takes to process it. You must not use paper material, i.e. that which contains cellulose, at all in these processes. And the reason for that is that the cellulose will interact with the hydrogen peroxide and it will degrade its effectiveness as a microbicidal agent. So if you've wrapped your load in paper, then as the hydrogen peroxide tries to penetrate through the wrapping material, it will in fact become degraded, and it will be of no value in trying to sterilize the load that's contained within the pack. There are other issues. For example, you need to be conscious of possible corrosion. Hydrogen peroxide is a very strong oxidizing agent, and it can corrode certain materials. So it's very important to follow manufacturer's instructions to ensure that the medical device you want to sterilize is in fact compatible with this type of process. Now, I mentioned that some of these processes employ what's called a plasma phase. So let me very briefly try and explain what a gas plasma is. Well, if you consider matter can exist in 4 states, and if we take water as an example, the basic state, the most lowest energy state of water is ice, and that would be a solid phase state. If we then add thermal energy to that block of ice, it will melt and it will become liquid water, and that is the second phase, or the liquid phase of water. If we continue to add heat energy to the liquid, then it will turn into steam, and that's the gas phase of water. Now, if we were to continue adding ever more energy to that body of steam, then eventually the molecules would begin to dissociate and form free radicals and ions, which are highly reactive and will react very nicely with any microbicidal contaminants present, and therefore that is essentially what a plasma is. It's a highly energetic, dissociated gas which will interact with any biological molecules present. So how does a hydrogen peroxide process work? Well, most of the sterilizers on the market will begin with a liquid solution of hydrogen peroxide, and that will be a solution in water. And often stabilizers will be added to prevent the hydrogen peroxide solution degrading during storage. Now, that liquid solution is often presented in the form of a cartridge, so it might be a single dose cartridge or it might be a multiple dose cartridge. But the idea behind that is to avoid the operators having to handle liquid hydrogen peroxide solution, because it's obviously quite corrosive. So once it's in the sterilizer, when the machine is ready to begin a cycle, a dose of hydrogen peroxide liquid solution will be passed through a vaporizer, where it is turned into the vapor or gas, and therefore within the chamber we will have a mixture of hydrogen peroxide molecules and water molecules. And it's quite important to recognize that we do not have pure hydrogen peroxide in the chamber, but rather this mixture of water and hydrogen peroxide. And then when that vapor or gas comes into contact with a cold surface, such as our medical device, then it will condense and it will form a microlayer on the surface of the instrument, and that is effectively what will kill any microbial contamination that's present. So here's another polling question. Do you believe the water concentration is an important factor in a successful hydrogen peroxide sterilization process? So you can answer yes, no, or if you're unsure, tick that particular box. So if we have a look at the poll result, then wow, 100% of people believe that the water concentration is an important factor. That's very interesting. I was just reading today the chapter in the new edition of Block, which is obviously the decontamination Bible for people like ourselves. And in that chapter, there was a discussion about the fact that moisture might not be that important. Well, I agree with all of you. I think the water concentration is an important factor. So let's have a look at how we go about specifying, validating, and routinely monitoring any sterilization process. So this is not just relevant to hydrogen peroxide, it applies to any sterilization process. And essentially, sterility assurance is achieved by carrying out three basic steps. The first is specifying. And when we do that, we're writing a detailed specification explaining what the equipment is, the process that it's going to generate or create, and then how we can monitor that process both during validation and routinely. Now, in an industrial setting, there will be teams of engineers and technologists who will be able to write such a specification from scratch. But generally speaking, in a hospital setting, all of this documentation would have been created by the manufacturer of the sterilizer, and he will be able to hand you a large manual containing all of the necessary information, which would include the process definition, the maintenance schedules, the engineering drawings, and so on. So normally all of that is pre-prepared before you even buy your sterilizer. The next step is validation. And this is where we actually prove that the sterilizer is delivering what we want from it. And that takes place in three steps. The first is installation qualification. Now, when a new sterilizer is placed in a department, we would typically do some checks to make sure all of the services have been correctly applied and installed, and that the machine is essentially as intended by the manufacturer. The next step would be operational qualification, where we would run a series of usually empty chamber tests or tests where a defined challenge device might be used in order to show that the basic cycles on the sterilizer are operating correctly. And then the next step, probably one of the most important steps, is performance qualification. And this is where we demonstrate that the cycle that the sterilizer is capable of delivering will in fact process the equipment loads that we want to sterilize in that particular sterilizer. So that's performance qualification, and it's where we show that the sterilizer and the loads we want to sterilize are compatible with each other. The final step is routine monitoring. I often hear people say, well, my sterilizer is validated, therefore I don't need to do any routine monitoring. Well, nothing could be further from the truth, because obviously the validation exercise establishes a line in the sand, but it doesn't tell you anything about how the machine is going to perform in the future. So it's also important to have a sequence of routine monitoring steps in order to show that the equipment is functioning on a load-by-load basis according to its specification. Now, if we do all this correctly, then we will inevitably get a sterile product. So another polling question: do you believe a hospital can validate the loads it processes in its hydrogen peroxide sterilizer? Yes, no, or again, unsure. So, wow, again, 100% response rate, suggesting that the member in the audience, the one member in the audience, believes he or she can sterilize, validate the sterilizer. I certainly hope there's more than one member in the audience. So let's now concentrate a little bit more on routine monitoring. So this applies to any sterilization process, not just hydrogen peroxide. The first thing we need to understand are what are the process variables. They used to be called critical process variables, but if you look in the ISO definition, you find that they're now called process variables. And the process variables are those characteristics of the process which cause microbicidal action. So, for example, in a steam sterilization process, we know that exposure time and temperature in the presence of moisture are our process variables. So those are the characteristics that we need to monitor in order to ensure that the sterilization process is effective. Now, for hydrogen peroxide, the process variables would be time, temperature, and hydrogen peroxide concentration, or as many manufacturers will report, the dose of hydrogen peroxide that's been delivered. Now, the dose is essentially a calculation based on the area underneath the hydrogen peroxide concentration curve on your process diagram. Now, I'll explain that in a bit more detail later on in this presentation. Now, as we saw from our survey, most people now agree that moisture is also a process variable. And so it's important to understand whether or not we have the correct amount of moisture present in this sterilization process. So how can we ensure that the process variables have been applied correctly and that we are achieving the correct levels, the parameters for those process variables in order to ensure the process is effective? Well, there are basically three basic techniques that can be used. The first is the use of physical measurements, and we can use time and temperature recorders, which will monitor the time and temperature of the process and provide us with a record. Many manufacturers, sterilizer manufacturers, will also include a UV spectrophotometric method for measuring the hydrogen peroxide concentration actually in the chamber. So that's another measurement that can be carried out. Other manufacturers might use a pressurized estimate of the hydrogen peroxide concentration. We can use biological indicators, which are essentially a preparation of a viable microorganism, usually a bacterial spore, which is resistant to the process, but which is ultimately killed by that process if the process is effective. And a biological indicator will inevitably react to all of the critical process variables of our process. We can use chemical indicators, which are essentially combinations of chemical reagents which will react to varying degrees with the process variables, and usually are designed to give a color change at a certain level of exposure. So again, they will give a colour signal to tell us that the process has been acceptable. So in order to ensure that our process is effective, we need to really have a schedule of tests which we would use in order to monitor the process on a routine basis. The first element of this schedule would be a means of monitoring the function of the load, or not the function of the load, but rather the function of the sterilizer for every load that we want to sterilize. And many guidance documents describe the use of biological indicators, usually in combination with a process challenge device, in order to do this. And that would be used in every load. There are also guidance documents which talk about the use of pack monitoring indicators, and these are usually in the form of chemical indicators which are designed to demonstrate that sterilant has penetrated into the instrument set. And these are obviously useful for the end user because, again, usually the operating room personnel are trained to look for that chemical indicator and ensure that it has changed to the correct colour. We also need exposure monitoring indicators, again usually chemical indicators, which are in the form of tape or labels which will change colour and give a signal to everyone that that particular pack has been exposed to the sterilisation process. It's very important to use those kinds of indicators. We still see in the literature even today, both the press, the popular press and the scientific literature, articles which describe cases where non-sterilised surgical instruments have arrived in theatre and they've actually been used by the surgeon. Now, the monitor and checking that exposure monitor before use would ensure that that does not happen. And then, of course, to tie all of this together, we should really have a good quality system which describes the procedures that are going to be followed and the records that will be kept for future audits or examination. So let's very quickly look at biological indicators for monitoring every load. Well, traditionally, biological indicators would often take several hours or even days to incubate before you would get a result. But nowadays, with the rapid readout biological indicators, it's possible to get a result in a matter of a few minutes, anywhere between 20 and 30 minutes. And you can see on this slide that some of the major manufacturers, Steris, ASP, 3M, Terragene, will all provide a rapid readout indicator. Now, most of these indicators rely on a common indication technology. And what I've tried to do in this slide is explain how that works. So basically, vaporized hydrogen peroxide biological indicators usually contain Geobacillus staurothemophilus spores. Now, we know that those spores have associated with them an enzyme called alpha-glucosidase. And this alpha-glucosidase is capable of metabolizing a non-fluorescent substrate which is included in the growth medium. So as these spores, as they start to grow and produce this enzyme, they will effectively metabolize or eat this substrate. And as they do that, they release a fluorescent compound which can be detected in very low quantities by the autoreader technologies that the manufacturers supply. And these autoreaders are essentially very sensitive fluorimeters, which are picking up the formation of this fluorescent byproduct of bacterial growth. So essentially, if the autoreader detects the presence of these fluorescent compounds, then that's direct evidence that the bacterial spores are growing, and therefore that we have a growth positive and therefore a process failure. And in many cases, you can carry on incubating those vials for several hours or days, and they will then give a traditional colour change, which many people will be familiar with. So let's have a look at some of the chemical indicators that are available. So if you look at EN ISO 11140 Part 1, which is the standard for chemical sterilisation indicators, it describes 6 types of indicator. The first are type 1, which are these process indicators, which will be placed on the outside of every pack. And these are designed to give you a signal that that particular indicator, that particular pack has gone through a process. It doesn't tell you anything about the effectiveness of that process. It will simply tell you whether or not somebody pressed the start button. The type 2 indicators are specific test indicators, such as the Barry-Dick test, which many hospital practitioners will be familiar with. Type 3 indicators are single variable indicators. They have limited utility because they're designed to only react to one process variable. So they don't really tell you anything about the full efficacy of the sterilisation process. And then we have 3 other indicators, type 4, 5 and 6, which are called multivariable indicators, integrating indicators and emulating indicators. And these 3 categories are designed to be placed inside packs and to give you a signal that sterilising conditions were achieved at the point of placement. So it gives you a good idea that sterilant has penetrated and caused those indicators to change colour. And of course, those indicators would be read by the operating room staff who are going to use the surgical instrument set during surgical procedures. So here's another polling question. Do you use chemical indicators inside the packs you sterilise in your vaporized hydrogen peroxide sterilizers? So again, a 100% response rate. So that's very encouraging. I know in some jurisdictions, not all of the guidance documents will actually require the use of internal pack indicators, but it's good to see that practitioners listening to this talk are following what I think is best practice. So what I want to talk about now in a bit more detail are the requirements for vaporized hydrogen peroxide indicators, which is described in that standard I mentioned, 11140 Part 1. And I'm going to focus particularly on type 1 process indicators and type 4 multivariable indicators. Now, in order to test these kinds of indicators, you would use a very special kind of exposure apparatus called a resistometer. And this is not really like a true production sterilizer, because it's designed to provide very carefully controlled exposure conditions within the chamber. So for a type 1 chemical indicator, in order to show that it's giving a correct pass result, you would expose that indicator to 2.3 milligrams per litre of hydrogen peroxide vapour at 50 degrees C for 360 seconds. And when you expose the indicator to those conditions, it should show you a pass result. You would then check to see if it is capable of giving a fail result. And in order to do that, you would keep the concentration and the temperature the same, but in this case, the exposure time would be 7 seconds. Now, for a type 4 indicator, the pass and fail test conditions are dependent upon the stated values which the manufacturer provide. So in this case, the standard doesn't actually tell you what the test conditions should be, but rather you have to look at what the manufacturer says, what conditions will cause a pass. So using the same test conditions that I used for the type 1, say we have a type 4 indicator with a stated value of 2.3 milligrams per litre, 50 degrees C and 360 seconds. Then we would expose our type 4 indicator to those test conditions and we would expect to see a pass. In order to test to see if that indicator can show a fail, we would reduce the hydrogen peroxide concentration by 20%, the temperature by 3 degrees C, and the holding time by 25%. And under those test conditions, we would expect to see a fail. So, do all chemical indicators of the same type perform the same? Well, what I'm going to do now is this latter part of the talk is describe some tests which were published in the Central Sterilization Journal in the last issue. And the title of the article is Evaluation of a Number of Chemical Indicators for Monitoring Vaporized Hydrogen Peroxide Sterilization Processes. Now, the purpose of this study was basically to look at 8 commercially produced chemical indicators of either type 1 or type 4 category. In phase 1 of the study, checks were made to see if the indicators gave the correct response in pass and fail conditions according to EN ISO 11140 Part 1. And then in the second phase of the study, we checked the response of those indicators when we reduced the exposure conditions individually. So for the time of exposure, we reduced that by 20%. And then in the next set of tests, we reduced the hydrogen peroxide concentration by 20%. And in the final sets, we reduced the temperature and the time of exposure by 10%. These are the indicators or the products that were tested. You can see they're supplied by a variety of manufacturers from around the world. And the method was essentially to use a modified Sterilucent PSD 85 litre sterilizer, which was able to deliver test conditions, very stable test conditions according to the ISO standard for resistometers. The samples were mounted on a sample holder, which was essentially an acetate sheet with cutouts, such that the indicator or parts of the indicator ink were mounted in the chamber-free space of the sterilizer. And then this sample holder with the test samples was mounted about 100 to 50 to 100 millimeters above the vaporization inlet port, which you can see just at the very base of the chamber on a metal mesh holder. And this is actually showing you how the exposure was carried out. So essentially, the chamber, once the chamber was sealed and the samples were mounted inside, the chamber was evacuated to a very low level. Hydrogen peroxide was then injected into the chamber, which gave rise to a rapid rise in concentration. And then that was held for a period of time. And you can see that the because a single dose of hydrogen peroxide was injected, the actual concentration gradually fell away, but it was in fact within the tolerances required by the ISO standard. And then at the end of the exposure period, the chamber was evacuated, and that reduced the hydrogen peroxide concentration to a very low level. So the measurements that were carried out was that, first of all, we measured the target peak concentration to make sure that that was being correctly achieved. We measured the average concentration during the exposure period. And then we measured this dose or area beneath the exposure curve, which is delineated by this red area. So you can see this is essentially integrating the exposure conditions in terms of milligrams second per litre of chamber space. And many manufacturers, sterilizer manufacturers, will report the exposure conditions in that way, essentially as an AUC. So the samples, once they're exposed, were analysed in two ways. The first was by visual examination, and this took place in bright daylight, in direct sunlight. The second way was by measuring the actual colour using a reflectance spectrophotometer, and this instrument reported 3 colour coordinates which describe the position of a colour within this 3-dimensional space that you can see in the sphere here. Now, just to try and explain that a bit, the L star value tells you how white or black the colour is. So a pure white colour would have an L star value of 0. The A star represents the red or green nature of the colour, and then the B star value represents the yellow or blue colour of the indicator. So you can imagine any colour can be described using these LAB values. So just to try and explain this in a bit more detail, here's some plots of the indicators that were studied before and after exposure, and these are A star and B star plots. And so, for example, the shimmer indicator started red, and then after exposure to the hydrogen peroxide, it went yellow. So you can see the plotted point migrating from this red colour here over to the yellow part of the A star, B star graph. And similarly, the 3M trimetric started blue, and then after exposure, it ended up pink. So you can see again the migration of that colour in terms of A star and B star values. So here's a polling question. Do you think all of the results will show that the chemical indicators tested will respond appropriately to the pass and fail test conditions? And again, yes, no, or unsure. I'll just give you a few more seconds. Oh, well, yep, that's good. We've got some response there, and it's very interesting. It's almost a 50-50 split between the yes and the no, and then we've got a 30% who are unsure. Well, hopefully this next section will explain and give you the answer to that question. So let's have a look at the results. So what this slide is showing you are the visual interpretation of the type 1 pass and fail results. So on this left-hand panel, you can see the exposure conditions, which should give you a pass colour change on the indicator. And then on the right-hand panel, we have the colour change from the fail conditions. And you can see that these two indicators gave appropriate pass and fail colour change. They were well differentiated. This particular indicator, you can see a slight difference in colour, but unfortunately the reference colour in the instructions for use was a dark orange. So in both these cases, although they are slightly different, they would be interpreted as a pass. And for this indicator, again, you can see a slight difference in the depth of red of the indicator bar, but in both cases, the indicator is red rather than this orange reference colour, and so this particular indicator is giving a fail in both those test conditions. Here's the results from the type 4, and you can see in these group of indicators that we are seeing a difference. Now, I must state that this one in the middle does actually show a better colour change when it's visually examined. The colour reproduction on the photograph isn't that brilliant. Whereas on this lower one, you can very definitely see a big difference between the pass exposure condition and the fail exposure condition. This particular indicator, although there is a difference in colour, it's very difficult to differentiate. You can just see that this fail is slightly bluer than the slightly greener pass. And this indicator, again, is very difficult to interpret. The colours are very similar. Here's the results of the type 1s when we changed the individual variables by a certain amount. So hydrogen peroxide 20% reduction, time 20% reduction, and temperature and time 10 and 20% reduction. And you can see for these type 1s, there's very little difference in the colour that they change to when they're exposed to those reductions in the process variables. For the type 4s, you can see that these two indicators, again, didn't really differentiate between those 4 different test conditions. This middle group was able to differentiate certainly the reduction in time and temperature of exposure. And this particular product shows good differentiation between the pass condition and the 3 reductions in the test conditions. Now, I can also show you those results in terms of A stars and B stars plots. So what you can see in these graphs are essentially numerical representations of the colour swatches that I just showed you in those tables. So if we look at product A, we can see that numerically there's a good differentiation between the A star and B star measurements for the pass in green and the fail in red. But there's very little difference in the measured values where we actually changed the exposure conditions individually. The same would apply to product B. You're still getting some differentiation, not quite as much as with A, but again, with the changes in individual characteristics, there was very little colour differentiation. The same would apply to products C and D, where there is, again, reasonable separation between the pass and the fail, but not too much separation, if any, between where the individual test conditions were changed. And for the type 4s, with product E, you can see there's very good differentiation between the pass and the fail, and some differentiation between the pass and when we changed the process variables individually. With product F, again, there is some differentiation between pass and fail, but not very much between the results from when we changed the variables individually. And then product G, again, differentiation is observed between pass and fail. And there is some differentiation between the samples when we look to change the variables individually. Product H didn't really show any difference in colour, no matter what changes we made to the test conditions. So let's now consider some conclusions. Well, what about the value of type 4 versus type 1 indicators? Well, type 1 indicators are designed to be placed on the outside of sterilisation packs. And bearing in mind that the criteria for a pass or fail condition depends on a 353-second difference in the exposure time, i.e. 360 seconds for a pass, 7 seconds for a fail, they will offer limited value for detecting process failures when used as internal pack indicators. Type 4 indicators are for placement within sterilisation packs and show that sterilisation conditions have been attained at the point of placement. So they are by far the most useful indicators. How useful is a printed reference colour? Well, again, if that printed reference colour does not bear any relationship to the end colour that you're being asked to interpret, then it doesn't really prove very useful. So it's very important that any reference colour that's printed on a chemical indicator should have some resemblance to the endpoint colour that the user will be expected to interpret. So in summary, 8 different chemical indicators were tested. 2 of the type 1 CIs showed appropriate pass and fail results. Another CI gave all passes and 1 all fails. 2 of the type 4 CIs gave appropriate pass and fail results. Another showed slight differences in colour in pass or fail tests, and another gave the same pass or colour. So the overall conclusion is that users should ensure purchased CIs are suitable for use in their own situation, and that clear instructional material is available for the end user so that they can interpret the indicators correctly. So on that note, I'll open the discussion up for a Q&A session. I notice we've got a few minutes left.
Wonderful. Thank you so much, Dr. Kirk, for providing this wonderful, informative, important information. We do have a couple of questions that came through. The first one is can plasma be used in ophthalmology instruments and laparoscopic instruments?
Well, this again is down to the individual medical device manufacturer's instructions. What you will find is that when a medical device manufacturer provides instructions for use, he will include the types of sterilization process that can be used on those instruments. So it is very important that you look at the manufacturer's instructions, both of the medical device and the sterilizer, to make sure that the sterilizer that you're using is compatible with the medical device that you want to sterilize. And most of the medical device manufacturers and the sterilizer manufacturers will provide comprehensive lists of the types of instruments that can be sterilized and the process in which they should be sterilized. So again, most of these sterilizers will have a selection of maybe 2 or 3, 4 maybe different cycles. And again, it's important to make sure that you use the correct cycle for the medical device you want to process. Just extending that a little bit further, there are a lot of accessories that can be used with the surgical instrument sets. And again, it's important to make sure that that accessory, for example, porcupine mats, have been correctly validated for the sterilization process that you want to use. So basically the answer is check the instructions for the medical device that you want to process.
All right, thank you. The next question, what is your opinion for load release? Exclusive with biological indicators, or could you release with BI diary and other loads to release with type 4?
Well, this is, again, very regionally dependent. So if you look at some jurisdictions, you'll find that the local guidance, which may have been produced by a government department or by a professional association, will require that you use biological indicators to release loads. And in other jurisdictions, they will perhaps suggest biological indicators are of less importance. So again, I think it's important that you look at your local guidance documents. But I do think that particularly for these more complicated processes, it's quite important to gather as much information as you can using the different monitoring tools that are available to you. So the use, and certainly with the advent of these rapid BI technologies, you're not having to wait very long before you will get a biological indicator result. And similarly, chemical indicators that are inside the packs are really aimed at the use of the operating room personnel rather than the sterile service department personnel. So again, if you look at the WHO surgical safety checklist, and that's been adopted by the majority of operating room professional bodies, there is a check in that which requires them to ensure that the pack is sterile. And the way that I've interpreted that is that they should ensure that the packaging is intact and that the internal chemical indicator, which they would call the internal sterility indicator, that internal chemical indicator has reached its endpoint color. So we're talking about two different application areas, really. The first is the biological indicator result for use in the sterile service department, and the other application area is where the internal chemical indicator is of value to the end user to make sure that that pack has received a sterilizing process.
Thank you. And that is all the time that we have. Additional questions will be shared with Dr. Kirk directly for email response. Dr. Kirk, thank you so much for spending your Friday evening with us. It's been an honor and a pleasure to listen to your presentation, and we hope to have you on another Beyond Clean virtual event in the future. For everyone still tuned in, we have our final session coming up in about just under 15 minutes with Dr. Wava Truscott, and we will see you all shortly.
Thank you all very much for listening. I'm now going to have a... Thank you. Goodbye.